does not mean that this isn't important. You know, just because something doesn't come up day after day after day doesn't mean that's unimportant. It just means that's not a skill that's self-reinforcing like a lot of the other ones are. Okay, good, you're live. So I left you for homework with a question where I wanted you to determine the percent composition of water. And that's a little open-ended because it's just like I didn't give you any masses. I didn't give you anything. I just said, what's the percent composition of water? So what do you do? Yeah. Oh, yeah. Well, so you would ask for the note. But for people who did have the note, what do you do first if I give you a question like this that seems to be missing key information? Yeah.
I found the mass of H2O.
Ah, so you found the mass just of water itself.
Yeah.
Okay, could you do me a favor while I try and find a copy of the sheet? Could you do that on here for me? Thank you very much.
Shaking.
Okay, what unit is on that?
Great.
Phil, I may have to print another one out for you after and get you after. Sorry about that.
It's okay.
I don't know where I would have put them. But I wonder if I just recycled them and they're gone. Good. Okay, so the mass of a single mole, right? This would be 1 mole of water, right? But then that also represents our total mass of water, right? Now, if I'm doing percent composition, I need to know the mass of what and what. Yeah. Yeah. So in this case, what's the mass of hydrogen in water? Okay, so each hydrogen atom weighs 1.00795. Is that the number? All right. And how many of those are in water? 2. And so what does that leave us with? Nope, for this. What's 2 times 1.00795? Anyone do that? Have people done this? I should ask that. You got them?
That's 2.0159.
2.0159?
Yeah.
Great. And we also need the mass of what? Mass of oxygen. And how many oxygens are in a water?
1.
Just 1, so that's easy then. What's the mass of oxygen going to be? Yeah, but not quite so rounded. Very good. I mean, I understand that that is basically 16, but we're going to keep our significant digits here. So now to find the percent composition, which one do you want to do first? Hydrogen or oxygen? Okay, to find the percent composition of hydrogen, what would we do? What would we do? Lauren, did you do this? I think you did. I think I saw you do this. So what would you do to find the percent composition of hydrogen? Yeah. That's fine. We'll get the same answer. 18 point. Perfect. And when you do that, what do you get? 11.1898. Yeah, that's fine. And for us, because obviously everyone's different, how many sig figs did we keep here? It looks like 5. 1, 2, 3, 4, 5. So 1, 2, 3, 4. So I'm going to round here. Again, yours may be different, right? It just depends on how many sig figs you kept as you went. But for what I happened to lazily write down here, that would be 11.190. But again, where you're rounding is going to depend on how many sig figs you kept. Does that make sense? All right, and then what would the percent composition of oxygen be? How would I do that? Two ways we can get that. Yeah. Very good. Divided by 18.0153 grams times 100%. And what do you get when you do that? What do we get when we do that? 88.810%. Great. How else could I have found that percent composition of oxygen? Good, because percent composition has to add up to 100. Good. Does that make sense? I know you weren't here yesterday, so the answer is probably, I have no idea what you're talking about, right? But once you get through yesterday's lesson. So in water, what makes up the majority of the mass of water? Oxygen, which makes sense, right? Oxygen is a relatively heavy element, right? Hydrogen, even though those two hydrogen atoms, only makes up 11% of the mass of water. So if I decomposed water into hydrogen gas and oxygen gas, 88% of the mass produced would be oxygen gas, and only 11% of the mass produced would be hydrogen gas. Does that make sense? Okay. Any questions about that? Can I send somebody on a magical mystery mission up to the photo? Would you mind? Okay, let me give you my keys. Sorry, I lost track of time, as I am prone to do. It'll say like physics, empirical formula. So today's topic is, it's one of the trickier ones in the course, I think. There's kind of two kinds of thinkers. If you are like me and you take well to like the mathy stuff, like where when we were doing the dimensional analysis and figuring out how many grams make up a mole and how many moles make up a gram, if that stuff comes quickly to you, then you may find that this lesson is a bit of a tricky one. And on the other hand, if that stuff is like, if it's the math you don't like, but you like sort of the conceptual stuff, then you may find that this one's good for you. Does that make sense? Today's topic involves math, but it's a bit more conceptual. And again, it kind of exists in a vacuum. We're going to learn it today. It's important. It's something you'll need to do. We're going to do a lab based on Tuesday, which I'm going to post today for you guys. I just have to make sure I can borrow some crucibles from another school because, fun fact, I have crucible tongs. I have crucible lids. I have crucible triangles. I have crucible rings. What don't I have? I don't have any crucibles. There's just none in the building, and I'm not quite sure why. I'm assuming that somebody ate them. Does anyone know what a crucible is? I guess I'm saying this word over and over again. A crucible is, it basically looks like a little teacup or a little bowl. It's just a little bowl like that, and it comes with a little lid like this that you can put on it. And it is a place, and then you sit it on a clay triangle, which is just 3 pieces of clay held together with metal wire like this. And you sit it, yeah, that's right. And you sit it above a Bunsen burner. And it is a safe place to have reactions take place where you don't lose any of the reactants or products. Yeah.
Are you doing this lab on the side, teacher?
That's my plan, yeah.
Well, we're not.
What's that? Where you was? Oh, really? Would Wednesday be better? Okay, we can say that Wednesday. It was, but the original plan was to have this lab on Wednesday, and then time frames go all over the place. Thank you so much. I'm very appreciative. You're so good. Jeez. Well, it's appreciated. So, with no further ado, today we're going to talk about empirical formulae and molecular formulae. And it looks bigger than it is. I just left lots of gaps for all the questions in today's thing, so I can kind of break big. It's actually not a huge one. It's a quick thing to teach, but something that maybe requires a bit of practice to learn. You're welcome. Thank you. All right. By the way, before anyone asks, formulae and formulae, or formulae is another pronunciation of it, and formulas all mean the same thing. It's just the plural of formula. If you want to sound douchier and more pretentious, you can say formulae, which is what I do. Because I think if the shoe fits, you should wear it. But yeah, the Latin rules would tell you that the plural of formula should be formulae, so that's what I write. But the reality is, most people just put formulas, and that's okay too. Does that make sense? So if you want to change all of these to formulas, you go nuts. But nothing wrong with that. But I like it, so I'm leaving it. Okay. Today, we're going to talk about something called the empirical formula. Does anyone know what the word empirical means? If I do empirical research, what does that mean? Sorry? No, but I appreciate you guessing. Not imperial, but empirical. If something is empirical, it's something we have observed ourselves. So an empirical something, empirical evidence is probably a term you've heard before, is evidence that you've gathered yourself by observations. Does that make sense? So observed or seen for yourself. So what we're going to learn about today is, if I gave you an unknown compound in the lab and said, what is this thing? You would not be able to get necessarily its molecular formula, all right? But you would definitely be able to get its empirical formula with we can do that with relatively crude lab techniques. In fact, you're going to do it on Wednesday using just what we have here. So this is the first step in figuring out what the formula of an unknown compound is. Does that make sense? It's the first step in figuring out the formula of an unknown compound, is figuring out its empirical formula. And an empirical formula just tells you the ratio of one element to another. No, I promise you won't hate this, or you will, one or the other. But I think you'll be okay. It's not so bad. So here's what I mean. An empirical formula could tell me that there's 3 times as much sodium as there is hydrogen, or it could tell me there's twice as much carbon as hydrogen. But it doesn't tell me its exact formula. Because if you look here, C5H10 between hydrogen and carbon here. 5 to 10, which is 1 to 2. In other words, there's 2 hydrogens for every 1 oxygen. What about here? Same thing. So these are 2 totally different compounds. C5H10 and C8H16, those are 2 different things. One is called pentene, and one is called octene, but I screwed up and put octane, but it's octene. These are 2 totally different things, but they would have the same empirical formula. Their empirical formula would be CH2. All right, so the empirical formula you can think of as the lowest terms formula. Now, for an ionic compound, the empirical formula is the ionic compounds formula. Does that make sense? Because ionic compounds we always express in lowest terms, right? So for ionic compounds, they're one and the same. So if we're looking at something ionic, if you figured out its empirical formula, you have figured out its formula. You're done. But for covalent compounds, like octene and pentene and any other thing, it's just a first step. Why is that? What's true about covalent compounds? What's true about covalent compounds that isn't true about ionic compounds? Yeah?
They can arrange more than one kind of way.
That's right. We can arrange covalent compounds all kinds of ways. Making covalent compounds is like working with a Lego set. You can put them together a million different ways. And that's why for that, the empirical formula is just a first step. Then you'd have to figure out, the empirical formula would tell you, oh, for every 1 red brick, they used 3 green bricks and 1 blue brick, right? But the next step then would be to figure out what they actually built, because covalent compounds can build all kinds of things. But with ionic compounds, this would be the only step. Okay, so what we're going to talk about is how we find that. But I just want you to note that you can have many different compounds with different formulas that all have the same empirical formula. Is that okay? All right. So I want to break this down. Hydrogen peroxide. Now, hydrogen peroxide uses a naming system that we don't know. And some of you may know hydrogen peroxide's formula, but if you don't, have we ever seen a per in a covalent naming before? No, we saw a per with like the radicals, right? Like percarbonate and per things, but not peroxide. So we don't know how to make this thing. Okay. So with that in mind, we're going to have to figure out its formula. So what do? Well, in a lab, if I wanted to figure out what something was made of, I could break it down into its parts. What kind of reaction are we doing if we break something up into its parts? Very good. So I could take hydrogen peroxide and I could make it undergo a decomposition reaction. In fact, my grade 9s are going to do that next period at station 5. Nope, that's a lie, station 4. So when I did that, if I trapped the gases, I could end up with a situation like this, where I know I have 5.3 grams of hydrogen and 85.4 grams of oxygen. By the way, could you figure out the percent composition from this? Cool, that's not what we're going to do, but you could, right? Here's what we're going to do instead. We want to figure out its empirical formula. But remember, an empirical formula just tells me for every 1 atom of this, how many atoms of that, right? The one above was CH2, so for every 1 carbon, there's 2 hydrogens. So I have to go from grams, which does not count atoms, to a unit that does count atoms. What unit should I go to? Well, even that's just a mass. What's a unit that we know about that is a counting unit for atoms? Moles. Moles count atoms, right? Mole is like a dozen, only it's a lot more than a dozen. So because I want to go to a counting unit here, to count atoms, we're going to convert to moles. And it makes no difference which order you do it in. Which one would you like to convert to moles first? Which one would you like to convert to moles first? Hydrogen? Okay. So we'll do that one together, and then you can do oxygen by yourself. So we're going to figure out how many moles of hydrogen. And in case you've forgotten, typically when we're doing that, the letter we're going to use for number of moles is little n. Yeah, which is why we don't do it as a formula. We're just going to do dimensional analysis here. And you know how to do dimensional analysis. So we're going to talk about hydrogen first. So in this question, what do I know about hydrogen? I break down the hydrogen peroxide and I get 5.3 grams of hydrogen. But I don't want to know how many grams of hydrogen I have. I want to know how many moles of it I have. So what am I going to do? Bless you. And again.
5 moles by
Okay, but what am I, like, what should I physically write here?
like 1 mole hydrogen over.
Oh, so I'm going to make a fraction? What am I doing with that fraction in this number? Multiplying? Okay, and what goes on the top, Kevin?
1 mole of hydrogen.
So moles of hydrogen on the top. And what unit's going to go on the bottom? Grams of hydrogen. So you were right, by the way. I just want to follow my process so I know. Grams will cancel with grams, right? So when I do this, I'll end up with moles of hydrogen. But to do it, I need to put a number in this ratio that's true. So how many grams is a mole of hydrogen? That's okay. That's fine. But I don't want just one. I want decimal places. Is it 1.00795? Okay. And by the way, if we look, how many significant digits am I working with in this question? So I'm going to save myself some time, and I'm just going to make this 1.01. Does that make sense? Because I can. So why am I going to punch millions of digits into my calculator when I know I've only got 2 sig figs? Is everyone comfortable with that? If you write the whole thing in, we should get the exact same answer. Would you prefer I write the whole thing in? Let's put the whole thing in. We'll start adding, we'll start skipping steps later on. And how many moles is 1.00795 grams? 1. Good. And does that pass the say out loud test? 1 mole of hydrogen weighs 1.00795 grams. Cool. All right, what do I get when I do that?
I got 5.25, but of course
5 decimal.
5, which is just round to 2.
So 5.2 moles. Whoa. Okay, there we go. Okay, so 5.2 moles of hydrogen. And then I want to know how many moles of oxygen we have as well. So go ahead and take a minute and do that.
Lazy. That's a lot. That's hard.
Okay. Okay, how should I set this question up? What should I do? What should I do? Yeah. Okay. Perfect. Okay, so 1 mole of oxygen. And what's that weigh? 15 point. Great, grams. Great. And what units cancel there? Grams of oxygen cancels with grams of oxygen. And what do I get when I do that math? 5.3? Okay. Oh, and we have 3 sig figs here, don't we? So 5.34? Okay. Now, let's use our instinct here. So that means for every 5.2 moles of hydrogen, there's 5.34 moles of oxygen we collected. Now, this was a real experiment. These are real experimental data, which means, should we expect our numbers to work out perfectly? No. We're going to get numbers that work out close. They should be very close to perfect. But here's what we do. We have to figure out the ratio. We have to figure out for every one of this, how many of that, right? To do that, I mean, first of all, we can pretty much see clearly here. What's the ratio here? Really, like, we know these numbers aren't perfect, but pretty much 1 to 1. Okay? Here's what makes it tricky. There's no one way to test this. If it works out like a 1 to 1 or a 1 to 2 ratio, if it works out 1 to anything, then just dividing by the smallest one will give you the ratio. You have to watch for cases where the ratio is 2 to 3 or like 3 to 5 or something. Okay? So you have to finesse it a little bit. So there's a few things to try. So to figure out the ratio, the first thing to try is always this. Divide both numbers by the smaller number. Wait for it. There we go. So you can try that, and that will give you the lowest terms ratio. And if it is exact or if it's really close, so if it was like 1 to 0.95 or 1 to 2.95, you can round that. I don't want to, if it's like 0.7 or something, that's sketchy. That's not close enough to round. Does that make sense? So let's see what we get when we do this here. 5.2 divided by 5.2 is obviously just going to be just 1, right? We're dividing it by itself. Does that make sense? Divide 5.34 by 5.2. What do we get? Yeah, well, what do we get? 0.9.
You get 1.026.
Oh, right, of course. 1.026. Okay. So right there we can see 1.0 to 1. This obviously, and especially because how many sig figs do we have in this? Just 2, right? So this is a 1 to 1.0 ratio. So what is definitely the ratio here? 1 to 1. So what would the empirical formula of this be then? The empirical formula of hydrogen peroxide Who is telling me they love therefore statements? Who was it? There you go. Isn't that a nice one? All right, and what is it? What's the empirical formula if it's 1 hydrogen and 1 oxygen? Yep, so the actual way we write it would be HO. In other words, that formula tells me for every 1 hydrogen, there's 1 oxygen. Now, I just want to make a note. What does that mean the actual formula of hydrogen peroxide could be? Anything that fits that ratio. So the real formula could be what? Give me a couple examples. What's one thing it could be? Well, it could be just HO. That could in fact be right, but what else could it be?
H2.
Good. What's another one it could be? H707. Good. What else could it be?
H5207.
Very good. Okay, does that make sense? We do not know the formula of this thing. All we know is the ratio. Does that make sense? And I'm going to say, et cetera, et cetera. All right, it could be anything. So we don't know its actual formula. We just know its empirical formula. We just know its ratio. And in a lab, sometimes that's the best you can do. We would then have to send it off to do further testing to figure out its actual formula, right? In this lab, we don't have the technology necessary to get more specific than this. If it were an ionic compound, I wouldn't have to worry about it. but H and O form a polar covalent bond together. So we do not know what the formula is. Does that make sense? Tell me if it doesn't. Did you actually say 5,227, or did you just?
527.
Yeah, I didn't change that on you.
I think so.
That's weird.
Maybe I did 5,226. I don't quite remember. I just pulled a number.
Did he?
That,
That's just weird. That was my address at one point in my life. Anyway, that's fine. That was weird.
I did that.
And we were just talking about that with like phone numbers earlier.
Yeah.
But
We
that's.
were talking about like the other day how we used to find breakfast.
Oh, I wasn't even thinking of that.
That's what I
Are you stalking my past? If next time I say it, you say like the street name instead of a number, I'm really gonna know. Like, all right, pick some atoms, and you'll be like, look at the periodic table, spelling it out. I'll be like, okay, now you're creeping me out. Anyway.
All the fingers is possible to be spelled out.
Is it? I don't know.
You checking?
Yeah. No, it's not.
Darn.
Okay, so
The region's on there. So now we can not narrows it down.
Wow. Okay. I'm not enjoying this. Okay. So now I want to try again. This time we took some compound and we burned it, and we found that we had some compound. We don't know what it was, but it was 50% sulfur by mass and 50% oxygen by mass, half and half. Crazy, right? Does that mean its empirical formula must be SO? Why not?
Because they're more than masses.
Because they have different masses, right? A sulfur atom doesn't weigh the same as an oxygen atom. So we're going to have to do this question. Now, I haven't actually given you masses here, okay? But it's actually super easy. It's super easy because 50%, 50%. Since I haven't given you a mass, we could pick any mass we wanted. So you could do this with 12 grams and say 50-50 would be 6 and 6. But let's make it easy. Since they gave you percent, what total mass could we pick that makes this no math needed? We can just get going. Yeah, so just if I give you a percent composition, just assume again, you could pick any mass and multiply it by the percentages. But if you pick 100 grams, well, now you've just got the masses, right? So we're going to assume a 100-gram sample, which would mean that I have 50.0 grams of sulfur and 50.0 grams of oxygen. Does that make sense? Again, I could have picked any mass in the world and multiplied it by those percentages. It just strikes me that if we're going to pick any mass in the world, why not pick the easiest one available, which would be 100? But if you're a glutton for punishment, you want to make this question hard on yourself, make your total mass like 26.3 and go. Whatever. Okay, so I want you to try this question just like we did the last one. Can you do that? Okay. So follow the same steps we followed last time. Sorry? That's right. 50.0 grams of sulfur and 50.0 grams of oxygen, because this one actually works out to be 50-50. I remember seeing this question in a textbook once and being like, oh my goodness, they found an actual compound that worked like that works with those with 4 numbers. This is real thing. So I had to use that. Mm-hmm. You're going to figure out how many moles of each, and then we're going to figure out what the mole is. Now that we've figured out we have 50 grams of each, same question as the last one. 1.54 what? Those were 50.0, right? If you look, so given was actually 3 sig figs. You're totally right. Had it been just 50, you'd only have 1 sig fig, but I intentionally made it 1 sig fig.
Yeah, it's not, right. I meant to round it. I meant to round it.
Oh, wait, yeah. 3 sig.
Yeah, I usually am overheating.
Yeah, probably doesn't do that at all.
Like, I would rather come to work sick all week and at least feel good on the weekend. Yeah, that's stuff I wonder. I don't know my line again because we're living in Franken climate. It has no idea what it wants to be. And I've got to put my snow fencing up for winter. Cool. All right, now just like last time, what do we need? So what is the ratio of these two things? And we said that the first step to try is what? That's not saying that. It's not one of those. But what did we do to test it here? Yeah, spread that first. But multiply the smaller number and see if I can see. Nice. Good work. Nice. So what do you think the ratio is? Very good. So what would the empirical formula be? So here we said it was, here we said it was 1 hydrogen, so H, and 1 oxygen, so just O, so HO.
So it'd be HO2?
Well, what is it here? It's not
Oh.
H here, it's
SO2.
very good. Would you mind writing these out on here for me? Would you be so kind? Thank you.
I don't want to write my Oops.
Why'd we only keep 1 sig fig? Oh, we didn't. Let's do it. Okay, cool. So, yeah, I meant this one versus here. Good. Yep, you're good. 3 sig figs, 3 sig figs. Yeah, good. Very good. So what's the empirical formula? I don't know what experience that's into
Do you want me to
Do
write
you guys know
the?
that like the devices you use in your everyday life are just like what science fiction movies looked like when I was a kid? Anything about like you pull an iPad out or that tablet or like a phone or you like talk to Siri or like Alexa or whatever. Like that's like in when I was growing up, like they put that on a sci-fi TV show and that was like what the distant future looked like. That and flying cars, looking at flying cars.
And they saw they made it seem like we'd have holograms.
Do you want me to write this
in the
too?
event.
Yeah, please. That's true. There's a distinct lack of holograms, though. There are holograms. It's just not super common. But there is a Holocaust museum in Europe that took high definition, three-dimensional. So they used hundreds of cameras to interview these Holocaust survivors, and so they're actually able to make like these people here in high definition 3D like holograms that you can go sit and listen to. So it's this really kind of bizarrely immersive thing. Very good, thank you. I appreciate it. So can we walk through this? So we looked here at an example where we had 50 grams of sulfur, and we just have to convert that to moles. I'm hoping by now we're getting pretty comfortable with going from grams to moles, right? Trust me, you're going to do millions of it, so if you're still a little uncomfortable, don't be stressed, because you'll get there by the end, I promise. But we end up with 1.55 moles of sulfur in a 100-gram sample. And with oxygen, we end up with 3.2 moles. And so if we figure out what the ratio is there, 1.55 divided by 1.55 is just 1. And 3.12 divided by 1.55 is 2.01. Obviously, this ratio is, yeah, SO2, 1 to 2. Very good. How's that feel? Does that feel all right? So again, now, does that mean that this thing was necessarily SO2? What are the possible, so this is the empirical formula. What could be some possible formulae? What could it be? Obviously, it could be SO2. What else could it be? It could be S2O4. What else could this thing really be? S4O. Yep. You got it. And so on and so forth, right? S20O. Good. Very good. Etc. Etc. Also the name of my favorite pet store. Petcetera. That's clever. Even more fun, I once saw one where somebody had gone up and put a cardboard E on it, making it Petcetera, which was the name of like a really schlocky, like adult contemporary rock guy from the 80s. So anyway, Petcetera, solid name for a pet store. Okay. Now, do we have time? Yeah, we have time. Look at us. We got nothing but time. So the question is, once we've done this in a lab, how could we take that and figure out the real formula? And it comes down to a really cool device. I mean, there's other ways too, but one of them, and this is really quite interesting, is there's a device called a mass spectrometer. Now, we don't have a mass spectrometer, though if you take university chemistry, you will. You'll work in labs where you have access to mass spectrometers, but it's a really neat thing. It's just a device that it's basically an atomic slingshot. You just put a small sample into it, and it spins it at really high speeds, and then atomizes it, releases it. And so it's basically, it's like, imagine like a spray bottle. You know, you spray something and it spritzes out, but it does that while spinning. Now, if you can imagine, while it's spinning, the particles that are really heavy, they will travel further this way. Does that make sense? And the really light particles will land closer to here. So as they spin this thing and spray it out, they can figure out exactly how heavy each particle is by how far down the detector it hit. Light things will land here, heavy things will land down here. Does that make sense? You can picture it. Imagine taking, a golf ball spinning around your head and releasing it, and picturing what it would curve like versus like a wiffle ball. Does that make sense? Yeah, that's right. So I'm obviously simplifying this, but a mass spectrometer basically is a device that you can put a sample into, and it will tell you the molecular weight of all the compounds in it. Kind of cool, right? There's other ways to do this. We could use something called chromatography. There's a lot of different techniques, but one of the main ones we use is something called mass spectroscopy, using a mass spectrometer. And it will actually take a sample, an unknown sample. It won't tell you what's in it. It won't tell you what it's made of, but it will tell you its molar mass. It'll tell you how much each of those particles weighs. Now, if we combine that information with what we've already done, now we can figure a formula out. Does that make sense? So I'm going to give you a question where we've already got the empirical formula. And oh, I didn't use a subscript there. That was bad. Obviously, that should be written as sch3u4c. Comme ça. So this is an empirical formula, which means, again, what are the... Now, by the way, you probably already know the formula of glucose. I think you've taken biology, yeah? Well, don't say it. Don't say it. It can be a surprise. But probably if you've taken biology, you know the answer. But let's keep in mind, what are the possible answers? It could be CH2O. It could be C2H4O2. It could be C3H6O3, et cetera, right? Any of those could be the possible formula for this thing. Do we know which one it is? Okay. But what we know is that the real thing has a molar mass of 180.16. All right, so I take this thing, I put it through a mass spectrometer, and it literally just on its screen, it will show little peaks at each thing, and I look and I go, oh yeah, this thing has a molecular weight of 180.16. It just tells me. It's a black box, it's magic. That's why it costs thousands of dollars. Now we have to figure out, what does that tell us? What should I do? How can I make that number useful to me? So I know that my empirical formula is CH2O, and I know that the real thing weighs 180.16. What can I do? What do you think?
You can figure out the molar mass of carbon, hydrogen, oxygen, C. How that...
So find the mass of this, like CH2O.
Like each of the ones, and then figure out what amount of each of those with that formula.
So to be clear, we could guess and check, right? Like we could test this one, then we could test this one, and test this one, and just keep going. That's not a terrible idea. Let's start with the first one. Let's try CH2O, right? So let's find the molar mass of CH2O from our periodic table. Yeah, you can do it. I trust you. I have faith in you. Everyone has a periodic table, yeah? Yep. Yeah, just find the molar mass. What's carbon 12.011? You probably get your yellow one's going to give you more decimals than mine. I'm just going to use the white one on the wall. 1.00794. I want units, by the way. Yeah. I'm looking at you, Zach Brown. And I guess I can, whoa. One, two, three, four, five. One, two. That's what I got. Let me know if I'm right or wrong. How's that? Good, same? Great. Does anyone have any questions about how we did that? Okay, so Zach Brown is the real formula of glucose ch3u4c. No. How do you know that? The weights don't match. This weight is too big or too small? Okay, so the molecular formula cannot be ch2o. It's too small. Now, we could keep guessing and checking. Yes?
Can I grab those tablets?
Yeah, of course. They're on the side table.
Would you divide like the molar mass by the imperial formula? I mean, the imperial.
The empirical weight.
How much it weighs? Yeah.
Yeah.
And then you multiply the ch2o by that.
Oh, is she good? Yeah, I was just going to keep guessing and checking, but that's a great idea. I like that. Yeah, I think that's a very good idea. So you're suggesting that we try divide the molar mass by the empirical formula mass. And I'm just going to call that the empirical mass for brevity's sake. So when I do that, what numbers am I going to use, Ruby? What am I dividing by what?
180.16 divided by 30.0261.
Great. And what do we get when we do that?
6.00 something. 0.0011.
Sure. So the ratio is what? How many times bigger is the real thing than our empirical formula? 6. So glucose is 6 times heavier than ch2o. Well, what can I say then? What must be the formula of this thing? Of course. How's that? Now, it's hard to write that out as a set of steps, right? Does that make sense? It's kind of something you have to develop a feel for doing. It takes a bit of practice, right? A little bit of practice. In the time that remains, I'd like you to try and do it again on the next page. All right, so there's another question on the next page. And I think it makes you do both. I think it makes you find the empirical formula then find the molecular formula. Am I right about that?
Yes.
Yeah. So this one, it's challenging. It's a tricky question. But I have faith in you. Except for one of you. I think you'll be surprised too. It's Zach. I don't have faith in Zach. But I have faith in all of you who aren't Zach Brown.
Thank you. I really.
I don't understand why
Prove you
that
wrong
would boost
now.
your confidence.
Prove you wrong.
No, I like that. I like that. See, that's adversarial. Like, Orlando told me I couldn't do it. I'm going to do it. Forget that guy. I'm the opposite too. If somebody says something negative about me, I just fold. I'm just like, that person's obviously correct, and I'm incapable of ever doing anything meaningful in my life. I should probably eat chocolate. Oh, no, I forget to change that. South Lincoln High School. Oh, boo earns. I forgot. Where'd I put that?
We do not have a mass spectrometer.
Oh, sorry. Sorry. Does it make it harder that I'm going all over the place? I wonder if there's any high schools that do have like high-end analytical chemistry machinery. Probably like Ridley. Ridley probably sends a letter home at the beginning of the year being like, every student must buy a mass spectrometer and a nuclear reactor. Do they? That's disappointing. I went to a trivia night at Ridley. I had never been there, but I have a friend who teaches it. He's the head of science, and he's a really good guy. So I went to a Ridley trivia night. And first of all, if you're ever hosting a trivia night, don't make one of the categories. So the trivia, like there were 10 questions each round, and one of the categories was Ridley history. And that's rude. People come in from different places. Like, how do I know who the... Really, one of the questions, like, who is the groundskeeper's shed named after? I don't know. Why would I know that? So anyway, but it was a beautiful place. It was really nice. But it was in the dining hall, and it was like Hogwarts. I think we guessed like the first groundskeeper, and we were right, but they wanted the name. So that's good. Nice. It depends on where you go and when you go. My parents are big trivia night buffs, and actually it's a lot of fun. So I tend to go. But this wasn't fun.
It's like when you go to
Yeah, sometimes there's music trivia, which is super fun. Okay, well, it's 2 questions in one. The first one is you have to find the empirical formula. And I've made it visible, so I've given you 4 things. But it's just like question 2. But instead of doing it twice, you have to do this one 4 times. Is that nice? Yep. Yeah, it's a good question. It's a challenging question. It'll take you some time. So you can pick any mass you want. What mass are you going to pick? If you say my social insurance number right now, you're pretty good. Pretty good. That number has no meaning.
Wait, are they all negative? Are the first 2 negatives and last?
No, it's just a dash. It's just a comment. I'm just telling you what comment. Because it wouldn't make sense to get a negative. I didn't even know what that would look like. Anyway, no, yeah. So it's not negative, so it's dashes.
Are they crayons?
Yep. Well, it's percentages. So since it's all percentages, you can pick any weight you want and just multiply that by all those percentages. But what's a really easy number? Like you have to know, right? Okay, the total mass 100, then those numbers are numbers. Does that make sense? In other words, since I haven't given you a weight, you can pick any weight you want to do this question. If you pick 100, well, 49.48% of 100 grams is 49.48 grams. 5.15% of 100 grams. But do you understand why?
Yeah.
How's it 30 already? Wow.
9:33. Okay, so you know those storage helpers that you get at your house or something, the ones that like a little spring on them?
Yeah.
I would always just like, when I was like 3 or something, I'd just be like slapping that thing while.
Those terrifying. Did your parents like want to like freak out? Those things are not quiet.
They're really loud. Terrifying. I just picturing it just like swinging your hand.
I have a Christmas one.
Oh, really? What's a Christmas one look like? Is it like
Literally
Christmas
sit there
tree?
for hours just.
It's a snowman.
Oh, that's fun. Yeah, that's not happening to those for my childhood home. I used to.
Why would it be? But if I go draw up, everybody knows, so like.
This one.
But every single step.
Yeah, that looks great.
I just got smooth jazz playing
Wait.
One, and then one. It was not here. Which photo is here? Here's Shannon. Let's see the Shannon. Sorry? Yeah, it's super early, which I know is. Oh, don't be scared. I just.
Don't be scared.
Don't be scared.
Don't be scared.
It's just a photo. Just a photo.
What is it that you will see?
Do you know there are people who believe that when you have the photo taken, it steals your soul? Don't be scared. They didn't give me a sheet for you, but that doesn't mean you don't. It may just mean. It may mean that
Oh no.
you might want to talk to Luch.
Yeah.
You know what it is? I've just submitted an early list of who I was going to fail at. But other than that, it's fine. I'm actually retroactively failing you in math. I can do that. I don't know if they told you that.
You can. What?
No. And I'm not going to fail you in this other. You know, I'm sure they just overlooked you. I will ask off of that today.
They've overlooked me so many times.
Oh, you
On
guys.
so many things.
Oh my God. I was taking off this room and this class list quite a bit.
In both classes.
They're just
They're
like,
trying to
"Oh,
keep
it's
us
really,
apart, but
we persevered.
we persevered.
That part's just harmonics. Yeah. I can't do that part. Close enough.
Something like it. I mean, I'm pretty sure he's actually just playing random.
Yes.
Behind it. And then that ridiculous face like. Ooh. I'm like, yes. And those lyrics, which that is just amazing. In around the lake, not the sky, the sky. I'm just standing.
You pay $30 and you pay to get pictures.
Sitting.
Should be free to get the pictures, but then child.
You would think, right? Yeah. Become a photographer. Photographers, you guys spend a bit of money on like equipment and stuff beforehand, but they charge you lots of money for stuff.
That's why I don't want to be a photographer, because then I'll be like, what? Because I know how like kids are.
making everything switch into one.
Was that upstream?
Where is it? Oh.
Peace. I don't want this in top. Just a window.
I had a kid at this just made me think. I had a kid at South Lincoln. He used to wear an Orlando Magic hoodie every test day in chemistry to try to butter me up. I thought it was funny. The basketball team. I used to think it was so funny every time.
I hate it actually basketball.
Yeah. So not a basketball thing then.
Are we? I want to hockey.
That should have been yesterday. That area.
Mr. Leonard, all of the calculations for this should be able to be done on a normal calculator, correct?
Oh, yeah.
Okay. Just so I know that I can get this done. Is that how you get them to learn chemistry, you serenade them?
I used to know. You know the solo?
Who does?
No. I know. This part that I like the part where they're not equal. It's like, yeah, they.
No.
Yeah, I love that. Yeah, that's my favorite. But the solo is,
I used to know it. Very slowly.
You can go.
Yeah.
I don't know, but that ends on the like.
Yeah.
I need to cover to get that in that.
I can't get those.
No, well, no one can because it's ridiculous.
Yeah.
Bye bye.
Sorry to cut your mood, but
Okay,
sign off those.
I would love to. Cut my move, that's my job. I'm gonna steal the pencil.
So yeah, just here and then after that.
So today, these guys are doing a lab activity.
Yep.
It's a pretty quick and straightforward one, and I'm gonna do a little demo at the end. Mainly, I just want them to do it kind of carefully and conscientiously, and not like crowd doing it. Because there's lots of. I am. But oh no! That's okay.
Wait, we're doing a lab today.
We are doing it.
Homework? We are.
How are we doing, guys?
Terrible. Please no homework.
Well, if you did you say will you have homework?
Yeah, are we gonna have homework? I did the science questions, but now they're just random.
Just random what?
I have them in the back pocket and everything.
Perfect. That's great. Then you shouldn't. You should finish everything today in class.
God, I have the science questions done.
But if you don't, then you'll have homework.
I could just leave it.
Yeah, that's fine. As long as I